Okay, thanks. This talk is going to be based on work by a few people. Juan Maldacena, you know. I also want to point out that Jafferis and Wall were former members here at the Institute. So let's imagine that we're on a spaceship, which is near a very large black hole in an extremely clean environment. So it's just us and the black hole. We can imagine throwing particles into the black hole, and based on what Juan told us, we can measure pieces of the Hawking radiation. So we can set up a type of primitive two-way conversation with the black hole. And if we do this for a while, we'll discover that it behaves a little bit like a computational device with very primitive input and output ports. That's throwing stuff in and measuring Hawking radiation. From a distance, a black hole behaves a little bit like a very powerful but non-programmable quantum computer. And this is crazy, because a black hole is pure space-time. And if you take your rocket ship and you allow yourself to fall into the black hole, then you encounter essentially empty, although curved space-time. In particular, there's no wires there, no quantum computer, there's no matter of any kind. There's nothing that seems to be doing the computing. So it has to be that space-time itself is somehow doing the computing. Now, we don't understand this as well as we would like to, but what I'm going to do in this talk is discuss one example where you can see space-time itself do a type of computation. The computation we'll discuss is called quantum teleportation. And I'm going to introduce that by presenting a more familiar computation, a type of protocol that we normally refer to as shouting. So, okay, Alice has just flipped a coin and she got the result heads. She wants to communicate that to Bob, so she just shouts it out. And Bob writes down what he hears. This is perfectly fine, but maybe it's the case that Alice wants Bob to know, but nobody else. In that setting, they can do something slightly more complicated. If we imagine that, to begin with, they share a pair of secret but identical code books, then Alice can communicate heads to Bob by just telling him that it's the opposite of what happens to be written in their code book, which was tails. Okay. So this is totally trivial, but it's going to be helpful to break it down into a few stages and abstract it a little bit. So in the first step, Alice takes her code book and the coin, heads, feeds it into some machine. The machine informs her that they were opposites from each other, so she shouts that out to Bob. Bob takes his code book, along with opposite, feeds it into another machine, and the machine spits out heads. And that was the thing that Alice wanted to communicate. Okay. This is a protocol which is known as the one-time pad, and it gets us a little bit closer to quantum teleportation. But in the next step, let's imagine that we move to quantum mechanics. So Alice wants to communicate to Bob the state of a quantum coin. And it's a little bit difficult to describe that, exactly what that means, but roughly it's a coin that's a little bit heads and a little bit tails. This funny symbol here is the notation that we use to denote quantum states. And the main thing about them for this purpose is that they're difficult to communicate by shouting. For example, Alice may not even know the state of the coin herself, and if she tries to figure out what it is by measuring it, she could change it. So the whole shouting protocol doesn't work at all. But surprisingly, there's a close relative of the one-time pad protocol that does work. And so now what we have to assume is that Alice and Bob start out by sharing a pair of quantum entangled code books. What that means is a pair of code books where they're individually in some quantum state that's uncertain, but they're definitely in the same quantum state. So they might both be heads, or both tails, or some superposition, but it's definitely the same. Quantum systems like this are known as entangled states, and they're regarded as a resource in the theory of quantum information, because you can use them to do something interesting, which we'll see right now. So the structure of the quantum teleportation algorithm is extremely similar to the one-time pad, so I've condensed all of the sort of comic strip into one panel here. Alice starts by putting her quantum state and her copy of this codebook into the machine. It does a type of comparison on them and gives one of four answers, 1, 2, 3, or 4. Alice reads that answer and shouts it out to Bob. He feeds that into a machine along with his half of the entangled codebook, and out pops Alice's state. So structurally, this is very similar to the one-time pad, but there's actually an interesting difference, which is that in quantum mechanics, states can't be copied. So to begin with, Alice has the state and Bob doesn't. And at the end, Bob has it, which means that Alice does not. Somehow she's lost her copy. And that happens in this stage here, where she feeds it into the machine, and the machine does what turns out to be a destructive measurement of her quantum state. So in this case, it's a little bit of a stronger sense of teleportation, that the information is destroyed by Alice and reconstituted later by Bob. Okay, so that's an introduction to quantum teleportation. In the rest of the discussion, we're going to focus back on black holes. So we'll focus on these two questions. So first, if entangled codebooks are a resource, what type of resource is a pair of entangled black holes? And can these be used to power quantum teleportation? And how does space-time accomplish that? So one ingredient in this is this idea that ER equals EPR conjecture of Maldacena and Susskind. The idea there is basically that entangled black holes are connected by a wormhole. That's this thing here, whereas unentangled black holes are not. So the top diagram represents the spatial geometry, not space-time, but just space, for a pair of unentangled black holes. Basically just a pair of separate pits that you can fall into. The second diagram represents the same thing for entangled black holes, and now those pits are connected by a smooth geometrical structure called a wormhole. There's a geometrical connection between the black holes. So the idea is that that thing is the resource that's related to quantum entanglement. Now, we're going to be drawing space-time diagrams in a second, and to make life a little bit simpler, we're going to draw diagrams for a slightly simpler geometry where we cut here. And we cut the spatial connection between the black holes in ordinary space, but we focus on preserving the spatial connection, this non-trivial one, through the wormhole. But for the algorithm to work, we're actually going to need to remember that they're connected here. And the way that we'll do that, to make things simple, is we'll give Alice and Bob a pair of phones so they can communicate with each other. Okay, so this is a space-time diagram, a lot like the ones that Juan was drawing. And the rest of the talk is just going to be small variations on this picture, so I want to try to explain it fully. So first, these two large white regions represent the space-time geometry outside these two respective black holes at the two ends of the wormhole. These zigzag black lines here are the singularity of the black hole. This is where time ends, and space-time cannot be extended. This is where you die if you fall into a black hole. And the gray region here is a region where you're definitely going to end up at the zigzag line, because as we learned, you can't travel faster than a 45-degree line, and any point here, traveling less than 45 degrees, will inevitably collide with the zigzag line. Okay, so if you imagine extending this geometry out beyond the screen, then we would have some huge white regions connected by a sort of small white and gray region. That's this thing. And this thing serves as a type of bridge between these large space-time regions. This is the wormhole. This is the resource that we're supposed to use to do quantum teleportation. Okay, one last ingredient. I'm going to draw a couple of trajectories here. So here we have Alice. She's on a uniformly accelerated trajectory, just staying outside the black hole on the left. And here's Bob. He's uniformly accelerated, just staying outside the black hole on the right. What we'd like to do is use this geometry to allow Alice to send a message to Bob. Now, your first guess is just to say, look, these things are connected through the wormhole, just shoot the message through the wormhole. And there's a problem with that, which is the following. If Alice sends a message in, so the message is represented by this green trajectory, that's the world line trajectory of the message, then since it can't travel faster than 45 degrees, it actually isn't going to make it through the wormhole. It's going to end up on the singularity and not make it out to this white region where Bob lives. This reflects a fact that is a known property of quantum entanglement. which is that it cannot be used by itself to send messages. Science fiction and science media and sometimes scientists are confused by this, but black holes have it straight. They understand that if you entangle two black holes, you can get a wormhole, but it has to be a non-traversable wormhole. Non-traversable wormhole is a little bit like a burning bridge where you can try to cross it, but it disintegrates before you get to the other side. So this doesn't work. But Alice and Bob have one leftover trick they can use, which is this phone that we've allowed them to have. And they can use that to accomplish the task. And here's how it works. So first, as before, Alice throws her message into the black hole. It initially looks like it isn't going to make it through, but a little bit later, she measures a piece of the Hawking radiation, calls up Bob on the phone, and tells him what she found. Using that information, Bob can do another operation on his side of the black hole, which results in a change in the space-time. The wormhole geometry gets a little bit bigger, and now it's possible for the signal to go from the left side to the right side. So a little gap opens up here, which makes it possible for 45-degree lines to make it from the left blue line to the right blue line. The space-time geometry has changed a little bit in response to these measurements, and that's made it possible to send the signal. So this is how space-time geometry implements quantum teleportation. And there's a little bit of a twist on the version that we saw in the normal teleportation setup with the machines, which is the following. Let's imagine that you want to teleport not the quantum state of a coin, but a whole human being. Then this is something that you might not want to sign up for, because there's a destructive measurement involved. You'll eventually be reconstructed on the other side, but I wouldn't at least want to sign up for the destructive measurement myself. I think philosophers are divided on this, but sort of my gut tells me no. And here we can see what's happening to the information, and it has a perfectly fine time. The experience of the information as it's being teleported from Alice's side to Bob's side is just free fall in empty space-time. It might be worried because it feels like it's falling into a black hole, but it turns out to be a traversable wormhole, and it makes it out safe and dry on the other side. Okay, so I haven't explained why this happens to the space-time, but we can get a hint of it using this English language analogy that Juan described. So here's a little piece of the vacuum here, and we have this word, hippopotamus. And the rules are, it could have been any word that's there, but it's some word. And if you happen to know what the word was, then what you can do is you can create a little bit of negative energy that makes the wormhole traversable. It's like, in the burning bridge example, throwing a little bit of water on it that delays the burning just a moment so that you can make it across to the other side. But you can't guess the word, so that doesn't help. However, Alice and Bob can work together to determine this word. So how does that work? Alice, on the left side over here, measures the first half of the word, which is visible on her side. And she discovers hip-hop. And she knows English very well, and she knows at least the only word that I could think of that starts with hip-hop is hippopotamus. So she guesses that the word is hippopotamus. She tells Bob. Bob now knows that this half-word automus is sitting there in his space-time, and he can vacuum it up. Vacuuming it up removes a little bit of energy and makes the wormhole traversable. Okay, so just to summarize these two questions that we considered, what is the resource associated to entangled black holes? It's this wormhole that connects the two together. It's a geometrical resource. And how does this help us with quantum teleportation? The teleported message goes through the wormhole. So as one final comment, let me just say that here we were discussing one particular example of what seems to be a very interesting relationship between black holes viewed as quantum devices and black holes viewed as pure space-time. As a community of researchers, we haven't completely understood this yet. We don't know where it's going. We certainly don't know what it's good for, if anything. But there's a number of people working on it, and I hope very much that it's going somewhere good. So thanks for your attention.